everyone. This is Dr.Aravind Rajan Ayagara, an associate professor at the Department of Aeronautical Engineering. Last time we were seeing what are the subsystems of aircraft, and we were to the point where we had discussed what are the propulsion elements or propulsion subsystems of an aircraft. So I'll repeat a bit so that you can have a continuity in my lectures. Aircraft systems are actually based on are divided into four major subsystems, which are known as airframe systems, vehicle systems, navigation, and communication systems. So avionics and mission control systems. Sorry. So when you see the first two, that is nothing but airframe and vehicle systems, are physical systems. Okay, we were dealing about physical systems in the last lecture, and we had already seen what are the airframe systems, and we had already seen what are the vehicle systems. In vehicle systems, we were actually looking into flight control systems, and the second one what we watched was propulsion systems. Today, we'll be watching what are the other subsystems, or what is the use other than propelling the aircraft or propelling the vehicle forward or giving the thrust motion to the aircraft. What is the second use of propulsion system? Okay, so first thing is the bleed air. Bleed air is nothing but you have the high pressure third stage and 10th stage and 13th stage compressors where you extract some air, that is nothing but air which is highly pressurized and at highly what it says at ambient atmospheric conditions, to actually use it for other subsystems in an aircraft. So what you see here is the bleed air, where bleed air is getting we are getting bleed air from two sources. One is the auxiliary power unit, and the other is the engines. So engines are nothing but we can extract it from the compressors. But APU is nothing but auxiliary power units. But where is auxiliary power unit? If you see the image over here, it is a tail. It is situated in the empennage of a section, empennage of the airframe. APU is nothing but a small turbine engine which has a compressor and turbine which it is used to power the hydraulic systems, and it is nothing but a generator, okay, which runs on aviation fuel, and it actually gives us power for hydraulic systems and other power control systems in the aircraft during its mission, during the lifetime of its mission. Okay, so this example is actually from Boeing. Sorry, this is from Airbus A340, where the exhaust is actually situated in the far end of the aircraft. So bleed air, as we can see, you are getting from APU and you are getting it from engines. So what do we use bleed air for? Bleed air is actually used for pressurization of the cabin. Okay, when you say in the cabin, because why do we need pressurization? Let us see a bit apart. And the second use of usage 1A, and you have the 1B, which is nothing but anti-icing system. Anti-icing system is a system of pipelines that you see in the leading edge of an aircraft, where you pass some hot air or hot oil, heated fuel, not fuel, hydraulic fluids or a heated air, to remove the ice, which actually can perturb the suction of flow or the formation of boundary layers for good lift and flow characteristics of an aircraft wing. And 1C is nothing but ECS. ECS is engine control system. Environmental control systems and cooling of the cabin. So we have seen three different uses of bleed air: pressurization, anti-icing system, ECS, and cooling. So pressurization. Why do we need pressurization? And when an aircraft is at a certain altitude, we all know through international standard atmospheres, that as we move up higher and higher in altitude, we actually the density of the air actually decreases. So we actually need pressurization, or bringing the aircraft, the ambient, the atmospheric conditions inside the cabin to a certain level where the humans feel well and good for just breathing, to avoid hypoxemia and other kind of stuff. Okay, so bleed air is actually used for it. And the next slide, we can actually see how it is done. Okay, so here you can see bleed air which is being taken from the sources, that is engine source 1 left and source 1 right, and you have the source 2, which is auxiliary power unit. Auxiliary power unit is actually situated at the far end of the aircraft, that is in the empennage. So what happens is these servo valves or pressurized servo valves actually collect these bleed airs from compressor stages, and then pass it to the first usage. Is the second usage what we have seen is 1B, which is left wing and right wing usage system, 1B-L and 1B right. We also have the air conditioning, which comes in the cooling, which is 1C. You also have 1C just to make sure it is a redundant system, and you also have the environmental control systems where you have what is going on inside the cabin. So this is an example of how the bleed air that we saw, the bleed air usage that we have seen in the last slide was actually just a representative. Right now, what we are seeing is it is actually a designed and developed concept that is being put into use by Airbus companies. The next vehicle subsystem that we are supposed to see is fuel subsystems. Okay, what is the first main aim of a fuel subsystem? Fuel system is to provide reliable supply of fuel that is required for the mission of the aircraft. Second, you have in the fuel subsystem also we have the characteristics that other than providing just some supply, we have refueling and defueling, which is highly important, and other in-flight functions. In-flight functions is nothing but fuel transfer for the maintenance of gravity, engine feed, which we need fuel to the engine so that we can propel the aircraft. We have we have the fuel measurement and fuel management system, from which tank should I take and where should I put this fuel and so on. And fuel jettison. Fuel jettison is a fancy word. What I can say is fancy word for fuel dumping. Fuel dumping, as you can see in the figure, which is from Airbus A320, you have a small outlet which passes the fuel in case of emergency landing. For example, if an aircraft recently, yesterday or day before yesterday, we have seen that an aircraft actually lost its engine at a certain flight, which was bound from Denver to Jamaica, Hawaii, Honolulu in Hawaii. So what happened was there were some issues with the engine and it got fired. So the aircraft was actually supposed to come back to Denver. It actually saved. Everyone was safe. There was nothing, no one injured. Only thing is the aircraft had returned to Denver at its mid-course. So when it returns to Denver, when you're landing, you need you have maximum takeoff rate and maximum allowable landing weight. Maximum allowable landing weight should be satisfied, and that is the reason why when an aircraft is coming back in emergency cases like medical emergency or some kind of in-flight emergencies, it needs to dump some fuel, which unfortunately we have no other means. So it needs to dump some fuel. That is nothing but fuel jettison. Please make sure when you are using or when you are designing or even when you are on your design board, you need to make sure that all these systems, all these characteristics given by or required by a fuel system should be, safety is a first concern. Okay. So in this figure, we can actually see what are the design requirements and what are the system functions that we need. Okay, and in the first level, you have the conceptual phase where you have the operator design requirements, which are from mission or aircraft requirements also, and airworthiness regulations, like which are being imposed by government agencies like Federal Aviation Authority or the Directorate General of Civil Aviation in India. So these actually have some regulations. When you're designing, you need to consider the operator design requirements or the mission requirements from the aircraft and the regulations as an input to your tank locations, fuel storage requirements. If this is my mission, if my aircraft is a long range aircraft or medium range aircraft, I need this much fuel, I need this much fuel in trim, I need this much fuel in reserve and everything. And also, you should also consider the system functions, which we have seen in the previous slide. You need to have refuel and defueling, engine and APU feed, fuel transfer, fuel jettison, which I'll be showing you in the next slide, measurement and management control. So all of these actually require some kind of equipments. Those equipments are fluid mechanical functions such as pumps, valves, and actuators, which enable the fuel to be transferred from one part of the aircraft to the other part of the aircraft. Sensors and electronics, which actually are a part of avionics subsystems, and pumps are actually a part of hydraulic subsystems, which need to measure, the avionic subsystems like sensors and electronics and software, they actually have to measure what amount of fuel is there and is it allowable or is it quite enough for me to complete my mission and so on. So this diagram, please do make note of this diagram because it is an important aspect of when you design a fuel system. And make sure that your fuel system is actually redundant. That means you need to have an escape route, plan A and plan B. So, for example, this is a case of fuel tank arrangement in an Airbus A340. We know that Airbus A340 consists of 4 engines, 1, 2, 3 and Four. It has four engines, and it is a long range aircraft, which was replaced by, which replaces the Boeing 777, which is a competitive candidate for Boeing 777. What happens is you have boost pumps, and these are in the to your left we have the equipment that is needed to make sure we all have all these characteristics of the fuel system are satisfied. In the last slide, we were talking about fuel transfer and fuel management system. For example, if you're moving forward and you have the slight shift in aircraft center of gravity, what happens is the pilot can change. He can ask the fuel from trim, that means which is at the aft end of the fuselage, to be transferred into the inner or outer tanks of the wing aircraft. Meanwhile, if he is sensing that there is some issues in the wing, he can again transfer. I'll make a new note. Yeah, he can again transfer these fuels to the aft trim aircraft. This is nothing but inbound and outbound transfers. And there are also another inner transfers which occurs only in wing. The one in blue, the arrows in blue, what you see is here. So it takes from outer to inner, and you have another from outer to inner to outer and outer to inner. These are the other kinds of transfers that you require when you are operating a flight. So here you can see that you have a surge, which is nothing but reserve fuel. Surge is used for fuel jettison, and you have another cell collectors, which are cell collectors are nothing but they are a set of electronic equipments which actually load the level of fuel that you have. Apart from these, you would be needing whatever you have hydraulic subsystems, which are pumps, and you also would be needing fuel valves. So Airbus A340, to operate its course, you actually have a total of 19 fuel pumps, different pumps, which are boost pumps, central transfer pumps, aft transfer pumps, and APU transfer pumps, and a total of 36 fuel valves. The next subsystem is actually hydraulic subsystems. I've noted in red that no fuel use should be allowed for hydraulic subsystems because hydraulic subsystems are the one which control the primary flight controls and the secondary flight controls. When we were discussing the flight control systems, we had actually seen what are the primary and secondary control systems. So I'm not going to touch these, but I'm going to give a perspective from hydraulic subsystem point of view. And I have also written that not degradation in performance. Okay, failure should not be allowed, but this means it is imperative that failure should not be allowed. But degradation can be allowed. But this degradation, so-called degradation that we are allowing in an aircraft, should be controlled degradation. Okay. Apart from the primary and secondary flight controls, we also have the utilities. In the utilities, you have the landing gear, you have the brakes, you have. When you are considering about civil aircrafts, you don't need aerial refueling and loading pumps. You have cargo doors and passenger stays. Passenger stays like when you open the downside of an aircraft. So you have all these systems which are being actually operated by hydraulic subsystem. So hydraulic subsystem is one of the systems where you need continuous operation, which should be highly redundant. In general, modern aircrafts it is advisable to use two subcategories two same identical hydraulic subsystems for the operation of an aircraft. But nowadays, modern aircrafts have been using more than 3 or even 4 some kind of aircrafts. You even use 4 subsystems, 4 similar hydraulic subsystems in terms of redundancy. Let us see an example of hydraulic subsystems. So how does it work? You have a couple of actuators which are being let us say that these are actuators which control my control surfaces like elevator or ailerons or some kind of elevator. You have a reservoir where you have the hydraulic fuel, HF, hydraulic fluid. So the pump that is supposed to take the fuel from a hydraulic fluid from the reservoir and give it to my actuators is actually connected through a gearbox to the gearbox of, here you have the engine. You have engine over here. So what happens is when there is a need, or when the pilot is actually controlling the actuator, he is actually giving a demand signal through fly-by-wire system or direct electrical system or even some old age mechanical system. Okay, so what happens is it actually sends a signal to the pump, which actually is driven by the engine gearbox, and it takes some fluid from the hydraulic generator and passes to the actuators as per demand. and you also have an accumulator where you can consider having some of the hydraulic fluid that is unused. Okay, here you can see I only have one system. But this system is actually not redundant. So, in case of a general modern aircraft, what I'm showing is you have this one, which is quite complicated. It seems to be complicated. Nothing but it is just a mirror copy of the system that we have seen in the previous slide. So, what you have here is you have system 1 and system 2, which are identical. So each of them are connected to, each of them have the accumulator. They are connected to the engine over here using gearbox, and they have a reservoir. They have their corresponding actuators. They have their corresponding heat exchangers and everything. Okay. So what happens is, if at all, let's say that my system 1 and system 2, my system 1 has failed. My system 1 has failed due to some some issues going on with the in-flight conditions. So what happens is, I cannot use this system. If I have only one hydraulic system, my flight cannot fly. I cannot operate the aircraft. So that is the reason why it is always better to have a redundant system which is having 2 or 3 replicas of the same identical principal system. So in that case, the second system kicks in and it passes the hydraulic fluid through all the circuit members as per the demand. So now we have seen vehicle subsystems. So in vehicle subsystems, we have flight control system, propulsion system, fuel system, and hydraulic system. And now what we have seen is all through the physical systems. We have considered airframe systems and vehicle systems. And the next class, we will actually be seeing what are avionic systems and what are their subsystems. Avionic systems and their subsystems. And further, going down further, we'll be seeing mission control systems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.